Hello everybody, this video is hopefully going to be a good overview of section 3.1 where we're going to start talking about polynomials. So we've been looking at some basic functions. We started out the course with the general concept of a function, and that a function is the central study of math, or one of the central objects of investigation of math, is because they allow us to predict, which is kind of the point of math, is you want to model a situation and then somehow be able to predict what's going to happen, on paper, without actually having to do the experiment. So a function is basically something that allows for predictability. So if we take the concept of linear functions, because we in chapter 2 we spent some time on linear functions, and we also spent time on quadratic functions. So chapter 1 was all functions, but then when we realized that's too general. If we're really going to get to study the specifics of a scenario and know exactly how it behaves, we have to really get down and get specific and look at all the little nitty-gritty details of functions. And so we looked at linear functions, which are of the form y equals mx plus b, and then quadratic functions, which add another term, and how do you plot them, all that stuff, completing the square. We did tons of that. So if we continue that pattern of y equals mx plus b, well, let me write that here. So linear functions take the form f of x equals, let me write this, instead of mx plus b, I'll write it as a1x plus a0. And then a quadratic function would be a 2x squared plus a1x plus a0. And then a cubic function, you just keep adding terms. A 3x cubed plus a 2x squared plus a1x1 plus a0. Quartic function, and so on. And then a quintic function is just a fifth degree. And I won't write them all. a1x1 plus a0. Okay? So this is what we've been looking at. In linear functions, we learned how to plot linear functions and how to model certain situations with linear functions. Quadratic functions, we learned the shapes and what the vertex is and different aspects of it. And then cubic functions is most books start classifying that as just a polynomial. So we start out, giving special names to things, but then once we get to the third degree or higher, we just say, okay, it's just a polynomial. And, that's kind of an arbitrary decision. Somebody way back when decided once you get past quadratic functions, just call everything after that a polynomial. One reason might be why they do that in books is because everything past a quadratic function gets very difficult to solve. We have a general solution to any equation that looks like this. We know how to solve any equation that looks like this. These are nice, well-behaved things. For this, you just kind of move things around and solve for x. It's not that big a deal. For this, you have two solutions in general. So you would have to say x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. This is the quadratic formula, which really is the same as completing the square. You can solve any quadratic equation by either completing the square or just using the quadratic formula. So we have these general solutions for finding the roots of these. For cubic functions, we do have it as well, but already you'll see it starts to get very ugly, and it has a name. It's called Cardano's formula, and you actually have to first do a trick to what's called depress the cubic. I think that's what it's called. Um, so instead you get it into this form, and I'm not even sure what that trick is, but you have to do it. And then with this, you can use the formula, which says all of the roots are going to be here. X is equal to the cube root of n over 2 plus the square root of n over 2 squared plus m over 3 cubed minus the cube root of negative n over 2 plus the square root of n over 2 squared plus m over 3 cubed. So already that's disgusting looking, and we're only in the third degree. All right, the degree of a polynomial is the highest exponent, and already this is the general formula to solve it. So things get very complicated very quickly. So nobody's going to memorize this. Only certain people with some sort of an issue would memorize this, or a mathematician who needs to study this for some reason. Most people learn this, and that's really as far as you can remember, because the formula is so complicated. So things get complicated very quickly. For quartic functions, there's a formula for it that I've never seen. Even I don't even know what it looks like. I believe for once you get to a fifth degree, it's been proven, and it was about 200 years ago, it was proven that you cannot solve anything of degree 5 or higher. There's no general solution. You can solve it. There's certain forms of it. Like if I have something like x to the fifth equals 1, then I can just take the fifth root of both sides and I get x equals 1. So I can solve a fifth degree polynomial, but I don't have an equation or a formula for the general solution for any fifth degree. So, anyways, things do get complicated, and if we follow this pattern, that's what I was saying. If we follow this pattern of adding terms and powers, then we can see that the general definition of a polynomial, as long as your exponent is a non-negative integer, 0, 1, 2, 3, or so on, any function that a function that can be written this way, a n x to the n plus a n minus 1 x to the n minus 1 plus a1 x to the first power, but we never write the first power because it's redundant, where a n is not equal to 0. This is called a polynomial function of degree n, where all of these a's are just the coefficients. So if I have something like 3x to the fourth plus 2x squared plus 1, then the coefficients are 3, 0, 0. I'm sorry, 3, 0, 2, 0, and 1. So the 0 coefficients we don't write, but they're there, but we don't write them. So, kind of a concept question. What do you notice about all the exponents? All of these exponents. Well, they are all integers and non-negative. And I'll say 0 or bigger. That's what I mean by non-negative. Just a fancy word. So that's basically a polynomial. It's just you have to have whole number powers that are 0 or bigger. So which of the following would be polynomials? I have 5x cubed plus 3x to the negative 2 minus x, x to the 1/2 plus 2x squared, and then this thing, 2x times x minus 4x plus 3. Well, this is not a polynomial because of that negative 2. One of the exponents is not a non-negative integer, so it doesn't work. Similarly, this is not a polynomial because of the 1/2 power. That's not an integer. This is a polynomial, but it's not written in this form. So polynomials can be factored, just like we've been factoring quadratics all this time. A polynomial can be factored, and that's what's happened here. This is a cubic polynomial that's been factored all the way. But we can multiply it out, and we would get something like 2x cubed plus some other stuff. And they would all be integer powers and everything. So this is a polynomial. So, one of the first relevant properties to look at about polynomials is how many times they cross the x-axis. And I can't really say right off the top of my head why we care so much about that. But it's always nice to know the roots of things. I think the roots are just simple cases of how you generally solve a polynomial anyway, so we just like to talk about the roots first, and then we know in general how to deal with it. So that's my best shot off the top of my head about why we care about the roots. So the number of times that a polynomial crosses the x-axis is called a roots. These are called roots or zeros. All right. So a number is said to be a zero of or a root of a function p of x if p of that number, r is what I wrote, is equal to 0. So now sometimes you can have a root. This is where we have the idea of complex numbers that we didn't look at very much. You can have a root that's there, but it's not a real root. So if we're dealing with only the real R2, then every polynomial has a root in the complex plane, but in the real plane, which is where this class takes place, there may be no root. So, we had quadratic functions. Remember that if the quadratic function never went through the x-axis, then I could use the quadratic formula x equals the opposite of b plus blah, 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 and I would get complex numbers. So what that means is that you get a root, but it's not a root that's real. So it looks like it never crosses the x-axis. It doesn't cross the x-axis, but there's still a type of number that would make it 0 if you plug it in, and it's just a complex number. So not something for you to worry too much about. So this polynomial here is, if I drew that a little better, is maybe of degree 3, and it crosses the x-axis 3 times. This is another one of, this is, I guess, degree 4, and I think it's degree 4. I'll tell you more later about how you figure out the degree of a polynomial just by looking at the graph. But you see this root here would be complex because it doesn't cross the x-axis. So there's a turning point here that it never goes through. So yeah. So what would that look like in terms of the actual algebraic expression? I'm saying here which of the zeros cross the x-axis. Well, any of the real ones would cross it, right? So this has real zeros, because if I plug in 4, I can tell, oh, I could just get 0. If I plug in -7 here, I'll get 0. So these zeros will cross the x-axis. This one, if I try to factor it, I would get x minus 3i times x plus 3i. So this piece of the polynomial has roots that are not real. So it might turn or do something there, but it's not going to cross the x-axis there. This one I don't know. I think it's probably has some real roots, but I didn't think ahead of time. So which of the zeros cross the x-axis? X equals 4, x equals -7, and then maybe alright, let me solve this. X is equal to 2 plus or minus the square root of 4 minus 8. Okay, see, so this one has imaginary roots. So the only ones that cross the x-axis are these two. And the rest of them, x equals plus or minus 3i. They're all imaginary roots. Okay? So we have an example. Let's list all the roots of this polynomial right here. And it's already very well factored for us. So we have x equals negative, x equals -5, x equals plus or minus 2. You got to get used, if you look at this, x equals plus or minus 2i, that's what this one is, and then x equals -2 plus or minus the square root of 4 minus 20. See, I'm just using the quadratic on this piece because it's a quadratic, but I can tell right here, because this is going to be negative, this is a imaginary root. So which of the zeros cross the x-axis? It's going to be x equals -5 and x equals 2 and also x equals -2. So there's 3 times it's going to cross the x-axis, or touch the x-axis at least. No, it'll cross it, I'm sorry. Okay, so this is a factored polynomial. It's not fully factored because I could do something here and I could do something here, but it's somewhat factored. If I were to fully factor it, I would have a bunch of distinct roots. Now we remember that sometimes we can get, when we're doing quadratic things, we would complete the square a lot. And why do we say complete the square? What does that expression mean? Well, you know it means to do something, but I take this thing and I divide it by 2 and then I square it, and that's what it means maybe in your head right now. But the reason we call it completing the square is because you're getting a perfect square out of the expression. So this is an example of a perfect square. X squared plus 2x plus 1 can be factored into x plus 1 times x plus 1. So this is really x plus 1 squared. So when the book or people use the term completing the square, they're saying get a perfect square out of whatever expression it is that you have, and that way you can solve the problem or find the vertex or whatever it is. So what I'm saying that is because when a factor of a polynomial only occurs once, we say that the root is distinct. Right? Should a factor occur n times, we say that it is a I don't know what I was going to write here, but it's of multiplicity. Oh, repeated root, probably. Repeated root of multiplicity n, where n is greater than or equal to 1. So the algebraic concept of multiplicity is strongly related to how the graph behaves, or I want to say turns, maybe, moves at each root. So the graph is going to either go through the root or go around the root or something like that, depending on the multiplicity. Really, it matters if it's even or odd multiplicity. That's what we care about when looking at the graph at first glance. Oh, I did not think about that. I hope that doesn't bother you. Oh man, you could see right through that. Okay. So we need some intuition of how the graphs of polynomial functions behave. So I hope this visual isn't too bad here. That was not smart. Oh boy. Well, let me just redraw this. So what I have here is I have this function. I have this function here. I have this function here, and then I have this function. And I was just asking the question, which of these represent polynomials? Let me draw a couple more. Okay, so which of these would represent polynomials? None of these first four would. A polynomial has to have an end behavior that goes either all the way to positive infinity or negative infinity on both sides. So and it also it must extend all the way through the x-axis. So this is not a polynomial, and also it has no sharp or turning points. There's a lot of properties of polynomials. It's continuous. It has no sharp points, so that's why this one's ruled out. It has a sharp point right there. It has at most n real zeros, so this one is not a polynomial. N being a number that's not infinity, which is a silly thing to say because infinity is not a number. It has to be a finite number, n. So this thing just keeps crossing the x-axis over and over and over again. It's a wave, so maybe probably a sine function or something. So this is not a polynomial because of that. This will never cross the y-axis, and that's not the behavior of a polynomial. It should be able to go as far to the left and right as possible. So this is some sort of a natural log function. This is not a polynomial for similar reasons. These two are polynomials. Notice that it's crossing the x-axis maybe several times, but it's a finite number of times. And it can go as far to the left and as far to the right as I want, and the end behavior takes it to positive infinity or negative infinity. It doesn't have to go to both, but it's got to go to either positive infinity or negative infinity or both. This is also a polynomial that goes to both positive and negative infinity. So that's some introduction to polynomials and what they mean. They are really very important structures in math, and they're used to model data. You can fit polynomials to data. In fact, Mr. Headley and me, we realized that there was a problem he was having in his robotics class, and we used Excel to model how far one of his robots was going to move based on some data that he had collected. And when we use the polynomial fit, which is something that statisticians and applied math people would use a lot. You have a set of data that maybe you're trying to model, but you don't know quite how to fit it, and it's not a line or anything like that. You can use a polynomial fit function, and it'll find a polynomial that'll go pretty well through all those points. And using that, we were able to model very well how much power he was supposed to be using to get these robots to move at a certain distance in a certain amount of time. I think that was the problem. But so anyways, they're used a lot, and I hope that was a good overview. Good luck.